All right, welcome back. We are Game 2005 in the fall 2020 semester at George Brown, and it's Game Physics, and it's Week 3, Part 1 of our broadcast. So we're sitting at Week 3 here. We're talking about, this week we're supposed to be talking about motion in two directions. By the way, you should be seeing our broadcast up on YouTube as well for those people who need YouTube for real-time closed captioning and stuff like that. There is a link up on Blackboard if you want to go there in the Week 3 content area to watch this live. And that's why I'm really using it, not necessarily because I want to record the stuff that's in this PowerPoint. Okay, so you can go and do that. So we're going to be talking about motion in two directions. One thing is, I was supposed to post an assignment 1 last week. I did post it, but somehow I don't know what happened. It didn't work up on Blackboard or whatever. So that's fine. We're a week behind. So I've got the assignment posted now, and I want to talk about it. Instead of it being due next week, where it was supposed to be due, we're going to just push these assignments off by 1 week, which means next week, when I give you assignment 2, as an example, it'll be due by week 7. So it'll give you just the same amount of time. It'll just shift everything in terms of everything that's due. So hopefully that's going to work for you. Okay. It means that your midterm test week is going to be busier, as an example, than it would have been as well. Just to give you an idea, on the midterm test, there will be some questions in terms of kind of things related to physics. So physics-related calculations, you will have to do that. That is part of it. There's also going to be questions that are going to be taken out of our out of the things that we're talking about over these weeks. So, for example, geometry and trigonometry, motion in one direction, two directions. It's going to cover all those things up until the midterm. There will be, again, just to let you guys know, there will be no formal lecture on week 7, but rather I'm going to be using it as office hours to work with you guys to answer any questions you may have and that kind of thing. So that's coming up in about a month, about 4 weeks from now. Okay, that's when it's coming up. So I'm just letting you know, you will have 2 attempts for your midterm. Again, it'll be offered to near the beginning of the week, and you'll have until the end of the week and for you to complete it. Okay, so that's what's happening. Let's take a look before we go into the detail of today's lecture. Let's go into our assignment details, which I reposted today. Okay, so assignment 1, motion in one and two directions. Right now it's due week 5. That's Friday, October 9th, 2020 at midnight. It is to be done with you and a partner, unless, again, you've been allowed to use up to 3 people. You have to get express permission from me to do so. If you somehow signed up and there's 3 people in your group, when I go through this later on today, I will just, and if you haven't asked me permission, and so far no one's asked me permission that I've approved to work in a group of 3, I will remove everyone from the team and you'll be unassigned. Okay, just letting you know. When you get unassigned, you won't be able to see the assignment submission box anymore. All right, so for those people who do not have a group still for some reason, I highly recommend you sign up to an empty group right now so that you can at least see the assignment. Worst case scenario, later on today, maybe through Discord, I'll get you a team that you can work with. Okay. So what are you going to be doing? There's a few parts to this one. So you're going to be working with, excuse me, I don't know why my throat today. You will be working with your partner in C++ and SDL. So you're not going to be working with Unreal or Unity or anything else like that. It's purely with C++ and SDL when you do the physics stuff. Okay. There's a few parts to it. One part is the physics problem, and then the second part is the physics simulation that you're going to be building in C++, followed by a video demonstration and then version control. Those are all pieces of your assignment. Let's go to the first part first, and you can read this documentation up online as it's already been released to you. Okay. So let's see what this says. Over a completely flat surface, a thermal detonator from Star Wars is thrown by a Wookiee, a member of the Rebel Alliance, towards a group of Imperial stormtroopers. The thermal detonator always leaves the Wookiee's hand with a speed of 95 meters per second, and the thermal detonator has a mass of 2.2 kilograms for your information. Suppose that the stormtroopers are 485 meters away. What is the correct angle for the Wookiee to throw the thermal detonator so that it reaches the stormtroopers? Okay, that's worth 10 marks. What is the maximum distance the thermal detonator could travel if you were going to throw it? If the Wookiee was going to throw the maximum distance, and is 485 meters even possible? As an example, this is something that you guys have to figure out. Include a short document, a report that includes a diagram that illustrates the problem and your solutions, right? Ensure you include appropriate labels and show your work. This is your math. Okay, so you're working in a group, you and a partner, chances are. My expectation is that you can, kind of draft it out on your own separately when it comes to this problem, so that when it comes to the test that you're going to have to do actual calculations on your own, you know the type of problems you're going to get. You've seen at least one of them. And I've given you some examples on all the PowerPoints in the back about the kinds of questions I'm going to be asking typically on a test. They're going to be mostly physics-related questions with physics formulas, okay? There's also going to be other questions on the test that are not formula-related, more of theory-based, okay? So that's the kind of stuff you're going to get on your test. But this will start getting you to think about, how do I use some of my formula, to solve this problem. Okay, so this is a physics problem. So you solve the physics problem on paper, and then you're going to do a physics simulation. You will use C++ and the STL framework to create a scene which simulates the motion of the particle. Because remember, we talked about modeling everything as a particle being the thermal detonator in this point, in the problem from part 1. Your application should include a start scene with labels that show the team members' names and student IDs, a button or other kind of control which would allow the user to go to the play scene where all the fun happens. Okay, that's what it is. So the start scene is really a place where you will be allowed to put in your names and IDs. All right. The play scene should include appropriate assets for the physics simulation. You should include a background image or tile map. Why? So it doesn't look completely white and boring. That's why. Choose an appropriate scale for your scene. So example, how many pixels per meter, and add appropriate variables and data structures. So this means that when you simulate your scene, how do you do that, right? It's worth 10 marks to actually do the scale and to run the simulation. Move the asset that represents the particles in the scene according to the problem described above. So, let's say you're going to put an image of a Wookiee and the image of a set of stormtroopers, and then the image of a thermal detonator, and then model the problem. See how it will actually move through your physics simulation. And then let the user activate the scene with some kind of button or other control. So start, like click or whatever. You can use a lot of different things for this, but please guide the user so that they know what they're doing. The user being me. Use appropriate label objects in your scene to show key statistics, which may include things like mass, position, velocity, acceleration, force, whatever other things that you want. And it says you may use IMGUI for this, as has been included in your template. We do have it in your template. It's just not activated inside of your STL template. You can also make your own labels, sliders, anything else you want, as an example, to make this work. Using IMGUI, which I'll talk about in a few minutes, is, I think, a good solution for this because it does a lot of simple things like buttons and an overlay and all that kind of stuff. It's really, truly up to you if you want to do it, though. So you don't have to use IMGUI. Allow the user to change variables. So stormtrooper distance, the speed that the thermal detonator is thrown, etc. Update your display accordingly. So if I modify the weight of my thermal detonator, the speed at which the Wookiee throws the thermal detonator, the distance from the stormtroopers and all that kind of stuff, then I should be able to modify those values, play with those values in my physics simulation, and then see what the results look like. So display the results. Things like what I'd be looking for is the angle of attack. So what is the angle of the Wookiee's arm? Is it going to be, kind of greater or more shallow? Is it a shallow angle? How does it look? Tracking the particle. As an example, when you track the particle, even though I say it's going to be, at 95 meters per second. I don't expect you to move 95 pixels per second or per frame. You need to make it appropriate, which means you need to scale it according to your screen size so that it can be seen and that it makes sense. If it's so fast that it runs kind of flies off the screen, that's not going to help me and it's not going to help you. Okay, so that's your physics simulation part. Please ask me questions around this, when it comes time to do this part. Video demonstration. This semester is going to be filled with video demonstrations for me, which means what you're going to do is you and your partner are going to use OBS or your favorite screen capture software, and you're going to create a small video presentation and put it up on Blackboard. You can use different ways of doing this. I know some people have used Microsoft Teams to get together and share their video and then record stuff. People have used things like Discord. They go into a Discord chat and they just kind of share their screens, and one person is recording with some kind of screen capture, and you record both people talking and discussing the code and that kind of stuff. I've seen different ways of doing this. It's really up to you. I'm going to leave it to you. I don't expect the videos to have post-processing effects. They don't have to be perfect in any way. What I do expect is that I can clearly see your screen. Okay, so your screen must be clearly visible. I need to be able to clearly hear each of the presenters. If I can't do those two things, then the video is pretty much useless. Okay, so can't hear you, can't see it. There's no need for the video. And you can't. I will not mark an assignment without a video. If you don't provide a video for your assignment, 0 marks. Okay, which means you must do it. It's worth 10% of your assignment anyway, so I'm paying you to do it. So please take a moment. The whole video should take no more than 5 minutes. You can go less, and you can go slightly more, like I'll allow a bit of a buffer. But beyond that, if you go beyond 5, let's say you do like 20 minutes, it's too much. And if you go like 30 seconds, the video's 30 seconds, you show like, I don't know what you're going to show with 30 seconds. It's too small. It's got to be able to satisfy the above requirements, which are, hey, show me your actual app working. Show me how this thing works that you built. And describe the code and functionality. How did you make this thing work? What formulas did you use from physics, if any? That kind of stuff. So describe that, and you have to be a little bit organized. Again, if you're just slightly above 5 minutes, it's okay. But I think you can probably, get it done within 5 minutes. You need a single slide, only one slide, to kind of start off the entire video, which says, here's a current image of me and my partner. Here's our names. This is our role. This is how we did stuff. Here are my student IDs, the course code, the course name, and what this assignment's about. That's the title slide. Only one slide, and the rest of the time you're just showing me your code in Visual Studio and showing me your demoing your actual app. Okay, so that is the video demonstration piece. And finally, version control is part of this thing. You must have version control as part of this whole thing. It's worth 5% of it. If you don't have version control, you'll lose 5% off the top. And here's your breakdown of marks. 30 marks to figure out the physics problem itself. So actually, for you to make a little document, there must be a document that has a diagram and the math should be there for your physics problem. Then there's 20 marks for the user interface of your physics simulation. So how it looks, 20 marks associated with that, as well and fields. And 35 marks for the functionality of your physics simulation. 5 marks for version control, 10 marks for your video presentation, for a total of 100. Okay, that's how it is. And this whole thing is worth 10% of your final grade. Okay. For submitting your work, you must have an MS Word or PDF document that shows your work for your physics problem, and include the name and student ID of each team member at the top of your document. This is important. Okay. A link to your working GitHub repository for your simulation, a zip archive of your project uploaded to Blackboard, as well as a link to your video demonstration. I recommend YouTube. You can use other streaming providers. Please do not give me a video. I don't want 200 megabytes of video. I won't even look at that. I can't. There's too many of you to look at. So please, be nice to me and give me a link to your video as opposed to the video, a big, massive video itself. That would be bad. Okay? So that is the assignment. I'm going to take questions now based on this assignment. So let's go to the questions panel now. I'm going to go to my chat and then start taking questions on it. So I've got some questions here. Both of us do a 5-minute video? No, you do. Tam, you kind of combine with the other person, and you together you do a 5-minute video. All right, that means both of you can talk. You should talk together. So one person can do the demo of the app, the other person can actually talk about the code, and then together it works out to be 5 minutes. If I upload a video to Blackboard, you should be able to watch it if the browser without downloading it. Can I do that? No. You need to put it up on a streaming service provider like YouTube or Twitch. Okay? I do not want to download or click anything off from Blackboard. Please don't do that. Blackboard is notorious for not allowing me to look at all the videos. All right? So please don't do that. And again, you can make your video unlisted. You don't have to make it public so that everyone can see it if you're nervous about that. It's more important that you just get it done. The part 1 of the assignment is to be done using normal method or using C++ programming shortly. The part 1 is to be done by actual figuring out the problems by hand. So in other words, you've got your problem, you get your physics formulas, and you do a little bit of research if you need to online, and you draft out what the solution to the problem is. I've asked some questions here about the Wookiee, for example, and you need to answer those questions in full sentences, please, with code. With math. All right. So, example, suppose the stormtroopers are 405 meters away. What is the correct angle for the Wookiee? And you can say the correct angle for the Wookiee is this, whatever this is, and here's the math to support that. So that will be typed out on the document. Yes, please type it out. And in previous iterations, I allowed people to take screenshots of their physical handwriting. That turned out to be a bad idea. Some people don't know how to do that, so I want you guys to all type it. Are not going to have any coding related question in midterm. There will not be any coding related questions in the midterm. The coding stuff is going to happen in the final test, where I get you to do a practical test. And you're doing coding related stuff throughout your labs. All the labs are coding related. Right, so with Spencer. Okay, so does that cover anything else? Any other questions around the assignment? Okay, guys, I'm going to take more questions. I'm sure you're going to have more of them as you come forward, especially those people who, for whatever reason, do not have a partner. That would be a bad outcome. All right. One question I always get for this one is, can I work alone? The answer is no. You need to work with a partner. Do we already know all the formulas we need? You're going to have them all today, Maxim. Missed the first few minutes because I'm still in the hospital. Sorry, Vincent. It's being recorded. You can always watch it later. Okay. All right. So let's get to this thing. The next parts. I'm going to move on now. Okay. I'm glad to hear that, Vincent. I'm sorry that you're there. So we talked last week about motion in one direction, and now we're going to extend that concept to motion in two directions, or 2 dimensions, if you will. I want to talk about what 1 dimension, 2 dimension means. Okay, people are confused about that. I've got a bunch of email that got sent to me, as well as Discord DMs that are like, you said motion in 1 dimension. What does that mean? Do you mean on the X and the Y axis? I mean the X or the Y axis. It's one or the other in the previous PowerPoint slide. Here, we're going to take the same formula that we talked about last week and extend them into 2 dimensions and break it down into 2 components, the X component and the Y component. Okay? Let's talk about this. So again, we talked about a couple things last week. We kind of differentiated between speed and velocity, right? Speed we talked about was a scalar, and velocity is a vector, right? It gives you both the distance and direction. That's what velocity does, and it's based on displacement, not on total distance traveled. Okay. Acceleration is the rate of change in velocity over a certain period of time. We talked about that. And velocity is the rate of change of location over time. Okay, so those are the things that we know from last week. So just a bit of a review. Gravity, we also know, tends to pull objects towards the center of the Earth. We also know that gravitational acceleration right, is there's a constant that we're using, which is 9.8 meters per second squared. That's based on Earth's gravity, and it's based on the fact that we are significantly close enough to the Earth that the distance isn't going to matter. In other words, it's not going to change 9.8 to something smaller because you're at the top of a mountain, as an example. We can assume for all of our equations and for the things that we do here in this course that gravity is always at 9.8 meters per second. However, I want to mention that inside a video game, gravity at 9.8 meters per second, and we've mentioned this before, may make your objects appear to float or floaty, because depending on the kind of pixels per meter ratio you kind of put into your game, it could maybe make it less competitive. You may want to use a higher value for gravity, for example, for falling characters, like 30 meters per second. So to make it so that the character falls much quicker. And why? Because you'll see, if you try it out, 9.8 is quite small. It does accelerate nicely, but if it's a small enough scale, for example, on a platform, you won't notice the acceleration happen too much. And in real life, we would tend to look like we're in the air. We've got a lot of air time. So kinematics in 2 dimensions, we're going to study the vector nature of position, velocity, and acceleration. We're going to treat projectile motion and uniform circular motion as special cases, 2 different things. Take a look at this little diagram that I've kind of shared with you. You can see that on the x component, if I was to project an object across the x-axis, notice that the separation in terms of x-axis, and this is an actual an image of a marble or some kind of a ball, a steel ball, as an example, being kind of projected out from the origin. You can see that on the x-axis, it's consistently the same amount. Okay, it doesn't change. However, on the y-axis, we see the separation of the ball on every time frame fall faster or further and further. And this is due to gravity's acceleration towards the center of the Earth, whereas there is no acceleration on the x-axis at all. This observation is something that we're going to be using throughout some of the things that we're talking about here in this section. So the position of an object, we can describe it by its position vector, where the change in, and notice it says r. R has also been used as in range. Sometimes we look at range or radius. There's different ways of looking at this, but you can see that the change of location, we can say that we're moving from one point to another. We have a directed change. We take the final location and subtract the initial location, and then we get the new vector. Notice that we get the vector that goes from A to B in that direction, right? Here it might be the path of a particle, and it could appear to be kind of like a circular path, but all we care about is the initial position and the final position. So again, we talk about displacement as opposed to the path. Notice I'm not path following here. I'm just going from point A to point B. I don't care about this other part in here, right? Because it's not about path following. It's about total displacement. In 2 or 3 dimensional kinematics, everything is the same as in 1-dimensional motion, except that we now must use a full vector notation. So both x and y coordinates as opposed to just the x coordinate. Okay? So example, now we can say that the average velocity, right, is based on the average position, x and y coordinate, or the difference in position from x and y over the difference in time. So time being a scalar and distance or position being a vector quantity. Okay? So that's a difference between what we did last week and what we did this week. Everything is a vector. Okay? The instantaneous velocity is the limit of the average velocity as we change time, or the change of time, or delta t, approaches 0. So again, when we read this this equation, we can say the limit as time approaches 0, the change in time approaches 0, for the change in position over the change in time is really the derivative of the velocity vector, sorry, the position vector over the derivative of the time scalar. Okay, So that's how it works. And you can see that as we're approaching, we can kind of create these secant lines as we're approaching the scalar, the tangent. This is a tangent line. We keep on coming closer and closer and closer until we get the instantaneous velocity, the tangent line, to the curve. And that's how it works. So, and that's what it says here. It says that the particle's path is along a line tangent to the path, which means tangent meaning right angles to the path. Okay. The magnitude of the instantaneous velocity vector is the speed. Speed being a scalar quantity. All right, if that makes sense. So the average acceleration of a particle, we talked about average velocity, now is the change in velocity, the velocity vector, over the change in time. Okay, again, these little marks here, they could also be seen as, sometimes we use little marks like this, and sometimes we use the arrow. The arrow means vector. These little marks can also mean vector. Okay. Again, the average acceleration, right, is equal to the change in velocity over time, the rate of change of velocity over time. That's what it is. And when we say the rate of change of velocity, it's velocity final minus velocity initial over time final minus time initial. And typically time initial is 0. Okay. So again, we're just talking about this kind of stuff. So as a particle moves, the direction of the change in velocity is found by this vector, right? So we can say that velocity final minus velocity initial is the change in velocity, okay? And the average acceleration then is the vector quantity directed along this path, okay? So you can see that we have a velocity vector in 2 directions now. It's not just about a matter of going in one direction or the other, right? And what ends up happening now is when we try and figure out our physics problems, as you'll see, we're going to separate the components. We're going to say, okay, on the x component side, what formula can we use? On the y component side, what formula can we use? And how do we get the final location of our object? Well, we're going to combine all the components of our, on the x and y components to get the final position. Again, there's other ways to do that as well. Okay, so the instantaneous acceleration is the limiting value of the ratio of the change in velocity over the change in time. So as time approaches 0. Okay, so again, we can use derivatives. So we haven't done calculus, but when we say derivative, it means that we can derive or get the acceleration from velocity. So if I have a position vector, right, and if I look at my position vector over time, right, then I can derive the velocity of my character or particle over time. I can do that. And if I have velocity over time, if I look at it on a velocity graph, right, as an example, or motion graph, I can also derive its acceleration over that time frame. So the first derivative we talked about last week of position in a position time graph is velocity. That's the first derivative. The second derivative of the position time graph, if we're going to look at a motion graph, is acceleration. And we saw that in that graph from last week, which you had those 3 things in there. It's the same thing here in 2 dimensions. Changes in a particle's motion may produce an acceleration. The magnitude of the velocity vector may change, and the direction of the velocity vector may change. So that's the 2 different things that we're dealing with this time around, as opposed to everything is in one direction, like we did in the last lecture. Let's think about these kinematic equations for 2-dimensional motion as opposed to 1-dimensional motion that we had last week. All right, so they're going to be very similar to 1-dimensional kinematics, but the difference is we have 2 independent motions, right? A motion across the x-axis and a motion across the y-axis, and it affects the final direction, final motion. Okay. So here is our position vector for a particle moving in the xy plane. Okay, typically what we do, and by the way, notice it's xi and yj. So y are, these are just the components of the vector. So typically what we say is the x component, when we say xi and yj, the x component and the y component. That's what it looks like, right? So the velocity vector then, that's for the position, right? So we add those two components up as an example when we want to get the position itself. The velocity then, the velocity vector can be found with the position vector, like we said before. We can take the derivative of the position, and what we get is the velocity on the x-axis, right, plus the velocity on the y-axis, and we can create the velocity vector itself. So I get two components, and then from those two components I can compose my velocity vector. Okay? Since acceleration is constant, we can also find an expression for the velocity as a function of time. We can still say that for velocity final is equal to velocity initial plus the acceleration times the time scalar, whatever that is. And in our case, when we talk about time, we think about frames. How many frames am I going to multiply the acceleration against in order for me to see that my velocity is changing? So again, changing over time. Okay? So that is, let's just go back. This is kinematic equations, second page. Page 3. The position vector, and this is, again, we're going to use this a lot, this form. It might look differently for you, and especially when you use the one for assignment 1, you pretty much can use, you know, when it comes to describing the motion of the object that's being projected, when it comes to projectile motion, we can use this. We can say that the position final is equal to the position initial. So example, let's say we're throwing a thermal detonator. Position initial would be 0, the Wookiee's hand, right? Then plus the initial velocity, 95 meters per second, multiplied by the time. How much time has gone on, right? We don't know yet. And then plus 1/2 of the acceleration constant, which is going to be gravity, times time squared. And so this equation is something that you can use to describe the parabolic motion of an object, of a, for example, of a projectile over time. So this indicates that the position vector is in the sum of 3 other vectors: the position vector, the displacement resulting from the initial velocity, and the displacement resulting from the acceleration. Okay. So here's a graphical representation of the final velocity. So let's just zoom in here for a second. Again, we're using vectors to describe this, but really what it's looking like is this. We have our initial position, right? And then what we're going to be doing is we're adding our vectors together, tip to tail. So we're saying velocity initial, right, plus the acceleration. Here's that v initial plus the acceleration times time. You get your v final. See how that works? So you actually have a final velocity at the end of the time value if x represents time, right? And notice how they break it down in terms of vyi, so velocity initial on the y-axis, that's this. Velocity initial on the x-axis, that's this component. Acceleration initial on the on the y-axis, right? And an acceleration on the x-axis. And you can see that you get a final position, a final vector. And this is the final Vy final, and you can see Vy initial. Okay? Vx final here. So this Vx final, this is Vy final. Okay, so you can definitely use vectors to describe the final position or the final velocity or the final acceleration as an example of your particle. All right. So here's so that was a representation of velocity and acceleration. Now let's take a look. Let's also include position. So now we've got position in there as well. Let's take a look at that as I bring this a little bit closer so you guys can see that in here. So again, we have our initial position. So here's the initial position. This is where it takes us, right? The initial position vector. Plus we add the initial velocity times time, right? So this is with the magnitude and direction. Plus we add half at squared. This is for the second formula that we saw. And then we get our final position at the end. And it makes sense. When we add them tip to tail, this is what happens. And you can describe each of the components of the formula on both on the y-axis and the x-axis one little bit at a time. So example, x initial, this is y initial, which gives us r initial, r being the distance from the origin or the initial position. And then we can do the same thing for x. Velocity across the x-axis times time. And we add the time component in there. Velocity across the y-axis times time. And you can see that you've got now the velocity vector initial velocity. And then you add 1/2 at squared to it. And you can see that x final is here. Ax t squared. Is there any kind of influence of acceleration on the x-axis? And the answer is no. There is no acceleration on the x-axis typically. So you wouldn't get any change here, but you would normally get a change with acceleration on the y-axis, and it typically wouldn't look like this. It would look like in a different direction, okay? Down. All right. There's various starting positions, and initial velocities can be chosen, and note the relationships between each change is made in either position and velocity, resulting in the effect that they have on each other. So this is the velocity and acceleration, and this is you can see how this part right here is kind of a subset, which looks like something that looks over here. It looks like that. There's a relationship. When it comes to projectile motion, and this is something that's going to help you for your assignment number 1 again, an object may move in both the x and y directions simultaneously, right? Which is what's happening on with a particle in your game world, right? You have both on the x-axis, pixels on the x-axis, pixels on the y-axis to get the final position from a vector perspective, x and y coordinates. And again, this form of two-dimensional motion we will deal with is called projectile motion. We're projecting an object from the origin somewhere else based on our kinematic equations, which is what's happening with the Wookiee and his his thermal detonator. So if it's a projectile can be described as any object which, when projected by some means and continues to move due to its own inertia or mass. All right. The only active force here in this scenario is gravity. So that's a projectile. We're not saying a projectile that has an engine behind it. I'm not talking about a rocket-propelled projectile. That's a different scenario. We're talking about a projectile like a bullet, or in this case, like a kicked football. Okay. Let's make some assumptions. The free fall acceleration is constant over the range of motion, and it's directed downward. So this is the assumption we're making. And this is assuming that there's flat Earth over the range of the motion. So we're not going to add peaks and valleys in there, to change where the object is going to land. It's also reasonable as long as the range is small compared to the radius of the Earth. Because if the range is very large, let's say, for example, I'm using a projectile that has so much velocity that it can go a very long distance, then the curvature of the Earth would also have an effect. No, we're not flat Earth. It's just we want to make it so that we're not going to take into effect the curvature of the Earth because of the small distance. It's going to be negligible, right? And same thing with air friction. Air friction is negligible. We're not going to worry about that in our scenario. With these assumptions, an object in a projectile motion will follow pretty much a parabolic path. And this path, keywords, is called a trajectory. Yes, flat Earth assumption is the way to go. So notice that the way projectile motion works, right? You have both components, right? You have components around the y-axis and components around the x-axis. Notice what it says. I'm breaking velocity down. What's my velocity across the y-axis? An upward velocity when I first start off. What's my velocity across the x-axis? A lateral or horizontal velocity. Notice that the velocity on the x-axis is consistent. You notice that there is the vector doesn't change size. Remember that from last week we just had the exact same size vector every single time because gravity does not act on the x-axis. It only acts on the y-axis for us, right, in our model. Okay? So notice what's happening is the velocity vector on the y-axis is getting smaller and smaller until it reaches an equilibrium at the peak or apex of the motion, right? And then as it continues, we're going to have the acceleration due to gravity on the y-axis increase until it hits the ground. Parabolic symmetrical motion. Okay. Now, there are three types of projectile motion we're going to be talking about in this section. Okay. The first thing is, if an object, as an example, is at the top of a hill and I'm kicking it or I'm projecting it off of the hill, right? So there's two ways of thinking about this. If I just drop an object off the top of the hill, if we have a target, an object which comes off a cliff horizontally, and this is the eventual histogram, okay? So this is what's going to happen. Which means in order to find the height of the cliff, if I want to find h, I need to know a couple things. What is the delta y? What is my change in y direction? Well, we can find that we're going to use v initial, right, across the y-axis times time plus 1/2 at squared. That is the equation we need to use for the y-axis. It's going to continue to change, and it's going to be influenced by gravity, where a is gravity. And change across the x-axis is going to be consistent. The velocity initial across the x-axis times time. Notice on the previous diagram we also had some other thing that I don't want to close my eyes to, called theta. Theta is the kicking angle. Okay, this is important. The angle of incidence, if you will. So what is the angle of incidence here? You can figure this out by the other components, and we're going to get there in a second. All right, so this is the first type of motion. So far, so good? We know, if we want to find information about this motion, we know that acceleration across the x-axis is 0. And that acceleration across the y-axis is negative 9.8 meters per second. So then we can use the next equation. We can say that velocity across the y-axis final is equal to velocity across the y-axis initial plus at. Okay, we can use that. We also know that at the top of Vyi is always 0. So the top, Vyi is always 0. That means the initial velocity on the y-axis, right? So this way we know that v, or velocity, is the square root of vx squared plus vy squared, right? It actually creates a triangle. Okay, and if you notice what this looks like, it looks like Pythagorean theorem. Okay. Here's an example of a gun in this scenario. I've got a cannon, and the cannon is on top of a cliff. And notice again that on the Vx, on the x-axis, I've got velocity that's 20 meters per second. Every frame, every frame, every frame. Seconds, one portion of a second, it doesn't matter. Every second, we're moving a certain amount of on the x-axis, and it's consistent. Whereas on the y-axis, again, you can see that the y-axis vector is growing until I hit the ground. And here it's showing that the velocity across the y-axis is near to or approaches negative 50 meters per second. Notice the negative because we're moving in a downward direction. Okay. And notice the positive on the x-axis as we keep on moving on the positive direction to the right. If I was firing my cannon to the left, then we could also view this as negative 20 meters per second. However, it doesn't suit us to do so. Why? Because if I was to reverse the gun and make it go the other way, the calculations just become more difficult to look at. The result is the same. Unless we have our model, and we must look at it from an east-west cardinal coordinate system. Okay, so let's think about this. An object in free fall will accelerate with gravity. Here's example number 1. To figure out where the ball will travel, we can look at the horizontal and vertical motion separately. Okay, consider a ball falling off a table. What should the equations of motion be? So I have a ball. It's falling off a table. How does it work? Right, kind of thing. Well, we want to break it down as an example, with these two equations, the first one. So your change in x is equal to vxt, and your change in y is equal to vit plus 1/2 at squared. Those are the first two things. So notice I'm breaking it down to these two components, right? If a ball rolls off a table at the speed of 3.2 meters per second and the table is 1.5 meters high, right? Let's sub in some of this information, right? So again, it's rolling off in this direction at 3.2 meters per second. So what is, if we were going to do this, let me just go into this a little bit closer. Can we fill in some of this information? So we're going to put some information in here. And it says, here's the questions. When does the ball hit the ground? And how far away from the edge of the table is the ball when it reaches the ground? Okay? And with what speed does the ball hit the ground? How do we know these things? Well, let's start subbing in the stuff that we know. We know that Vx, or the velocity across the x-axis, right, initial, is 3.2 meters per second. We know this. Why? Because there is no y component initially here. It's just kicking across the horizontal. How do I know this? Because if you look at the picture from the cannon, or some of the other stuff we've done, right here, there is no angle. We don't care about the kicking angle. The velocity across the x-axis is 20 meters per second. There is no velocity across the y-axis initial. Vy initial, in fact, is 0. That helps us determine where this stuff is. So we can say that, let's sub in some values. This is 3.2 times time, right? Whatever the time value is. Cool. What about this? So let's continue with the other analysis over here. We don't know the time yet, okay? But the next thing we want to figure out is, okay, what is Vi initial? Vi initial is 0, which makes this whole term of the equation also 0. Okay, why? Because if Vi is the velocity initial across the y-axis is 0, we multiply it by time. 0 times anything is 0. We get a 0 in the first term, right? 1/2 at squared. Okay, so we have this information, initial. We also know what gravity is. Gravity is a negative 9.8, right? So we know that half of gravity is negative 4.9. And I don't know why it gave me the plus minus, but that's okay. We can just get rid of it and put minus, right? Negative 4.9 t, right? Are we good so far? All right, so those are kind of the things we know, right? And how long is it gonna take to hit the ground? Well, what else do we know? That's the first question. When does the ball hit the ground? Well, we know that the table is 1.5 meters tall, right? Okay. So, as an example, can we not say that the final position then, so the change, this is the change on x, and the change in y. We don't know what the change in x is yet. We don't know what this is yet. But we do know what the change in y is going to be, no? Can we not know that the change in y, we figure out the y component first. We know that the change in y is going to be, or the position on the y-axis is going to be something like negative 1.5 meters. We know this. Could we not? Right? So if that's true, if this is negative 1.5 meters, we have information now and we can solve for t. We can start solving for t. Once we have t on this side, we can figure t on this side. Let's continue with this idea. Okay? So if we take this to the next level, we can say that t squared then is equal to negative 1.5 over negative 4.9. All right, so let's quickly figure out what that is. Negative 1.5. Come on, calculator. So let's just say we'll dispense with the negatives because a negative over a negative is a positive. So 1.5 divided by 4.9, all right, which works out to be 0.306. That's t squared, right? So t squared, 0.306, right? And we'll just take it to 4 decimal places just to be nice. So 3061, okay? And we know that t squared is equal to that. So that's t squared. So t. So what then is t if we take this further? How do I figure out t? I square root both sides. Now there's a challenge here, right? We'll talk about that in a second. If I take the square root of both sides, then what do I get as 0.3061? So calc. If I go to 0.3061 and I want to take the square root, it becomes 0.55326. Let's say 0.5533. So t then 0.5533 seconds. Am I good so far with you guys? So far this week, no mistakes. Last week, I didn't divide all over the same value, and that's why I got those wonky values. But this week, we figured it out, right? Okay, so if I know that on the vertical, it roughly takes half a second, 0.5533 seconds, roughly, to go here, then I can find the distance away from me. I know how long it takes to drop down. Then I know I can sub in this value over here, right? So I can take this one and sub in the value. So I can say that time is a known value. Now, we know that time is going to be equal to 0.5533 in this example, right? Which means that the total distance on the x-axis away from the root of the foot of the table is, let's do that again, 0.5533 times 3.2, which works out to be 1.771 meters. Are you with me? Check marks if you're with me. Someone put their hand up? I don't see a hand up. Most people understand what I'm doing. Do you agree, first of all? Would you figure it out this way? Right? Okay. Thank you for the feedback. All right, so now if you notice, we've answered a couple questions. When does the ball hit the ground? Well, it hits the ground, in long form you'd say, it hits the ground at approximately 0.5533 seconds. How far away from the edge of the table is the ball when it reaches the ground? It is approximately 1.771 meters away from the table. Okay, now the next one is, with what speed does the ball hit the floor? How do I know this one now? What do I do to figure out the last component of this one? What can I do? This is on you now. I have time, right? And I want to find V final. I know V initial, right? And I'm looking for V final, right? So what is my V final if my V initial? And do I need to use another formula for this? Come on, guys, I need your help. Otherwise, it's just going to be a download. I'm going to just tell you stuff, and you're not going to know what to do. What formula can I use for this? Take a look at the PowerPoint. I gave you it. Okay, here it is. Julian says V final is equal to V initial plus AT. Okay, let's use that one and see if this makes sense. Also, check to see if it makes sense, right? Because at the end of the day, right, we don't want an equation that we're going to use not to make sense. I'm just going to put it over here for us, okay? So let's use that equation. So V final, right? So V final, right, we'll say is equal to V initial. Sorry about the this subscript stuff. Plus AT. We don't need this part. We need AT, not AT squared. T. All right. So if this is our equation, I'm just going to move all these things over, right, to find out the last part of it, right, so we can see this nicely. And we know T, and we know initial, and we know what we want to find the final. Let's see if this works. So we're going to put this in here. Okay, what's our, and this is V final across the y-axis, right? What's V final across the x-axis? There's two parts to this, right? It's a vector. It's a vector, right? So it's not just on one part. There's both parts to consider. But let's suppose we just care about the y-axis for now. So that means V initial is 0, right? Isn't it? Ah, that's good. VF initial is 3.2. It's almost like I got to do two parts, right? So, and I'm looking at, look what it says. What is the speed of the ball when it hits the ground? I didn't say velocity. What's the speed of the ball, right? And speed on which direction? On the x-axis or the y-axis, right? If I look at the velocity, what is the velocity when the ball hits the ground? That's a different question, right? But let's just look at the velocity final on the y-axis. So velocity y final, right, is equal to velocity y initial, which is 0, plus at. Velocity initial plus at is negative 9.8 times time, right? Let's fill in those values. So it's negative 9.8 times time, which is 0.5533. I'm just gonna move this over a little bit so we can see it somewhere. Okay, that's we know that for sure. So we know that the Vy final, the final velocity across the y-axis only is, if we just solve that, is what? So we can get 0.5533 multiplied by 9.8, and this is a negative 5.4 something. Negative 5.4223. So 223. Negative 5.4. Oh man, why did it do that? Okay, so that's kind of where it is. Negative 5.4223 meters per second, right, in the y-axis. Okay, cool. If we know that, do we care about the x-axis? No, because the x-axis is not going to stop. It's not going to change. It's not going to change speed. The x-axis is still going to hit everything at 3.2 meters per second, right? Remember, the acceleration, right, as an example, does not affect the x component whatsoever. That's not going to change when it hits the ground. On the x-axis, it's going to hit the ground at 3.2 meters per second. On the y-axis, that's what we really care about. It's going to hit the ground at negative 5.4223 meters per second. So actually, it's going to be faster across the x-axis than it is across the y-axis. Make sense? Now that we know this, we know the velocity vector. The velocity vector is 3.2 negative 5.4223. That's the velocity vector. And then we can figure out the speed on the y-axis. Make sense? Hopefully it does. All right, let's continue. Yes, perfect world, no friction. Exactly. Kicking the ball, this is the second type of projectile motions. The first type is what we saw. You're off the top of a hill, you've got no angle. The angle's perfectly flat, so we can just ignore it, and we're just projecting a ball straight across from the top of a hill. Here's the second scenario. I have a kicking angle theta, whatever that angle is going to be. It's measured in degrees. It is an angle at which the projectile left the ground, or the angle of incidence, if you will, right? And then we have an initial velocity vi. It's the angular speed of a projectile at the start of its flight. This is both on the x and y axis. It's a vector vi, all right? Okay, cool. We can break the vector down into two components. Vx, velocity across the x-axis. Remember we said that we're going to use cos when related to the x-axis and and sine when related to the y-axis. So it's the two components are v cos theta, v sine theta, and that creates. We take the vector and we take a proportion of the energy. I want you to think of it this way. I have energy that I'm applying to both x-axis and y-axis. I want to take a proportion of the energy and I want to apply it to the y-axis, and a proportion of the energy and add it to the x-axis. This creates our triangle. Once I've got the triangle, I've got the angle of attack. I can figure out where the vector is going, where the projectile is going. Okay? I want to go from A to B. What's the time required to go from A to the apex? And how do I go from the apex down to the ground? This is symmetrical motion, my friends. We've seen something like this last week with Galileo. All right, so here we go. We have this idea. Vy final, this is the equation, plus Vy initial plus AT. We've seen this thing before, right? That is on the y-axis, okay? At the top, Vy is equal to 0. We know this, right? And if we do a proof, if we move things around, we know that Vy initial is equal to V sine theta. We're only caring about the y-axis right now. We know at the top of the motion that it's going to be 0. It's not going to go up or down. Vy final at the top is going to be in equilibrium. Plus gt, where g is gravity. So then we go to the next part of the equation. V sine theta, if we move things around, is equal to negative gt. And we can solve for t, and we can say that time is equal to V sine theta over gravity. That, my friends, is one equation we could use if we wanted to find the time it takes. Or we could also further break that down. The time traveled from A, that's the time travel from A to B. If I want to travel from A to C, we know that the motion is symmetrical, right? A to B, time it takes is the same time it takes from B to C. Therefore, we can take this equation and multiply it by 2 to find the total time. Okay? So this is an equation we use to find the total time it takes for the projectile to travel from a parabolic motion perspective. Okay. How can we find the maximum height? So those are two different things. Total time, maximum height. How do we find the maximal height? Well, we know that we can use an equation like v squared y final is equal to v squared y initial plus 2 times the acceleration on the y-axis and times the total displacement on the y-axis. Okay, that's what we get this equation. I'm not going to derive it for you, but we know that this is the case. If we move things around, we know also that Vy is equal to 0, right? Vy, velocity on the y-axis at the end, right, is equal to 0 at the top, at the apex, right? If we know that it's equal to 0, then we can solve for height, right? Where dy, this dy thing, is the height of the object the displacement on the y-axis, or the height, right? So we can say that the height is equal to v squared sine theta squared divided by 2 gravity, and just by doing some simple algebra. So that's the next equation you need to know for this type of motion. Okay, how do we find the range of the graph? Range is the horizontal distance. So we can call it range or distance. There's many, or displacement on the x-axis. We can use vxt. Why? Because acceleration due to gravity does not affect the x-axis at all. So that's how we can find the range, the total range. And we want to break vx down to v cos theta because we have an angle. In the scenario above that we were given 0 angle, right? We didn't care about the angle. So cos theta, remember where cos is? It starts at 1. When theta is 0, cosine is at 1 because it starts on the graph. Remember that? And again, to remember this as a mnemonic really carefully, if I have a graph, and you guys should be able to kind of map sine and cosine as programmers in your mind even. If you can't, you're like, Tom, I'm never going to remember this. Yeah, you can. It's not that difficult, guys. Cos starts like this, all right? Let's try that again. And graph it nicer than this. I don't know why I did that. I meant to do this one. So that's cos, right? So if I start like this, notice that when the angle, if this is pi from an angle perspective, if the angle is 0, right, then on the y-axis, it's equal to 1, right? That's the actual thing. When cos is 0, then y is 1, okay? So that's how it works. That's how we can figure it out. It's 1 when cos is 0. So because it's 1, right, if I go back to cosine, in the scenario where I have no angle, we don't care about cos theta. We have no angle. It's 1, right? Here we do have an angle, so we do care. It's going to affect the amount of energy that we're transferring across the x-axis because we have an angle. We're not putting all of the velocity across the x-axis this time. We're putting some of the energy for velocity across the x-axis and some of the other energy across the y-axis. So we're separating those two components, and we're going to get a triangle, right? The actual velocity, the final velocity, is the hypotenuse, right? Okay, we already know the time from A to C is 2v sine theta over g. That's how long it takes for the entire motion, right? And therefore, when we do some finagling in algebra, we can find that the total range is based on v squared sine 2 theta over g. Notice that there is no time component. Why? We've removed time. We know time is equal to this. And all we're doing is we're subbing in v cos theta times time. We know what time is. It's this thing here. We're just subbing that in. And then we get this equation. Okay? Okay, this is the third type of motion. So the first type of motion was off of a hill straight. The third type of motion, or second type of motion, is parabolic motion. Symmetrical, nice symmetrical motion, which is what I've asked you to do for the Wookiee. Symmetrical motion, right? Here's the third type of projectile motion. This is more complex. It's asymmetrical motion. Why? We have two parts of it. We have a trip that goes from A to B, from B to some point here where it comes down and there's symmetry. And then now we have initial velocity downward from here. So we have two legs of the trip. This leg and then this leg. Okay? We can break it down into two different problems, or we can use equations for the entire trip because of this asymmetrical motion. We have such equations. So again, we're looking for the time it takes. If we're looking for the time it takes for the ball to hit the ground from here to here, we want to go from A to C. Here the graph is not symmetrical, so the time from A to B is not equal to from B to C. Okay, it's not equal motion, right? We can use two different ways to get to the answer. We can use this way, where we know that y final is equal to 0. Okay? If we suppose that y final is 0 and not a negative number, right, in this case. If y final is equal to 0, then we can move our equations around. We know that the total distance is vit plus 1/2 at squared, total displacement, or range. We know that, right? And then what we can do is we can sub in values for the distance, y final minus y initial. And when we do our algebra, we can look at y final is equal to y initial plus vyit plus 1/2 gt squared. Guys, this is the same equation we've been using in different forms this entire time, from last week to this week. Okay? Instead of y final, we can say it's position. We can sub in position instead of y final if you want to. It'll be the same idea, right? Final position is equal to the initial position plus plus the initial velocity plus times time plus 1/2 at squared. Same formula over and over again. All right, so using the quadratic formula, which is what we're going to have to do, we can now calculate the time. All right, because if we figure things out, 0, which is the vy final, is equal to the height of the object plus the v sine theta, remember that's the y component, vyt basically, plus 1/2 gt squared, and we can use this to find out the quadratic equation for time, because here is the a component, we did this last week, this is the b component, and this is the c component. And we sub in those values into the quadratic formula to get two possible values of time. One of them is not going to make any sense. Okay? The second way to find the time for the object to hit the ground is to break the problem down into two parts, like I said. So the time from A to B is equal to v sine theta over g. We can figure this out because of the previous equations that we used. All right? to find the time from B to C, we need to find the height between A and B, which is the height equation, v squared sine theta squared over 2g, right? And we also know that y itself is 1/2 at squared, because y, we know that y starts off, y is going to be equal to 0, 1 part of y. And so the total height from B to C is this height, the height of the hill, plus the height of the apex. We know this from the total height from B to C, right? Or A to B, let's say. So if we know that what the total, we can calculate the total height of the hill plus the height of the apex. Now we know we can consider this a problem of the same problem from problem number 1, the first type of motion, projectile motion, where we don't have any angle again across the x-axis. The angle's gone, right? We only care about the falling object. So we're breaking it down into 2 parts, and that's what this does. So given that y max is the initial height of the mountain or the hill plus the apex, we can say that the time it takes from B to C, from here to here, is equal to the square root of 2 times y max, whatever that is, divided by g. Or we can look at it like this: the time A to C is equal to the time A to B plus the time B to C. This idea. And we can use equations to kind of come up with that time. Here's the range. To find the range, we can use Vxt. Again, that's not going to change. However, we're going to substitute V cos theta t because we don't have all of our energy across the x-axis anymore. We have part of our energy into the y-axis, like we said before. Okay? And using the last 2 formulas, we can find the time. To find the speed of the ball before hitting the ground, we have to do something different. We have to say that Vx is constant, so that all points Vx is the same, right? Just like we saw in that kicking formula. It's all the Vx components are the same because gravity does not act on the x component. It only acts on the y component, right? So if that's true, then Vy final is equal to V sine theta plus gt. We can have this formula, and we can, when we want to find the angle, we can solve for the angle by taking this equation here, and when we rearrange it, we have Vy over Vx. We can get the arc tangent to find out the kicking angle. Okay? So again, all we're doing a lot of times with these physics equations, these kinematic equations that you've been given, by the way, we didn't have to derive them in real engineering kind of physics. We derive all these angles from scratch. You know, we're not asking you to derive them or prove. We don't need you to do a proof or anything like that. That's not the kind of physics we're doing here. It's physics for game programmers more than anything else. Okay, and the calculus, we're just mentioning calculus right now. We're not actually getting you to do any of the calculus, which you would have to do in real physics. Okay, so then when you plug in the values for Vx and Vy, make sure the values are positive. This is important because otherwise we're going to get some weird, and I put this on its own slide because sometimes what we do is we don't do this and we get some really weird numbers that come out. Okay? Okay, how about the acceleration at the highest point? The vertical velocity is 0 at the top, right? The acceleration is not 0 anywhere along the trajectory. It's always negative 9.8 on the y-axis for every second. All right? If the projectile experienced 0 acceleration at the highest point, its velocity at the point would not change. But in this case, it does get negatively accelerated. That's why it continues to fall. When we analyze projectile motion, consider the motions as the superimposition of the motions of x and y directions. All right? And the actual positions at the time is given by the, again, distance final is equal to the distance or the range initial plus the initial velocity on the time times time plus 1/2 of at squared. This damn equation, we keep on seeing it in different forms over and over again. And by the way, this is good. It's good to find the same equation over and over again. That means we can use it, we can decouple it, and we can think about both on the y component and the x component. The initial velocity can be expressed in terms of its components. Vxi is equal to Vi cos theta plus Vyi is equal to Vi sine theta. We can break it down. And then the x direction has a constant velocity, right? Ax, the acceleration on the x-axis, is 0. Whereas the y direction is in free fall at all times, where ay is equal to negative g. This is even true of bullets. So again, if I fire a bullet with a muzzle velocity that's very, very high, if the bullet can travel far enough, it will fall to the ground, right? The trouble with bullets is, A, in real life, they're hard to track by eye. They're going faster than our eyes can perceive them, A. And B, they're traveling so fast that they're probably going to hit an object first before they hit the ground, like a person or a wall or something else, right? Okay, so here we just talk about the projectile motion of both vectors. I'm going to keep moving. And it talks about how to figure out the range and maximum height of a projectile. When analyze projectile motion, two characteristics are of special interest. The range, r, right, is the horizontal distance of the projectile. How long it takes for me, what's the distance between the origin on the x-axis and the final position on the x-axis. That's called the range. So whenever you say range in your mind, it's x-axis. And then h as the height. What's the apex of the motion, where Vy is equal to 0. All right? So those kind of are characteristics of the motion. So we can see that this is the, again, going back to the height of a projectile equation, we can use this, where height is equal to Vi initial, so the the velocity initial squared, sine squared theta initial, all right, over 2g. Okay, so that we can find out the height. And this equation is valid only for symmetrical motion. If we try and apply this equation for non-symmetrical motion, it's not going to work, right? That's why the 2g is there. The range of a projectile is slightly different. It can be expressed in terms of the initial velocity vector. So range on the x-axis is the initial velocity vector squared sine 2 theta, right, over g. So it's slightly different than what we had before. So these are like little shortcut equations you can use to figure out these different things that I'm asking. More about the range of a projectile. Here's something. Notice that there are symmetrical values, right, for the angle. So notice the angle. If I have an angle of 75 degrees here, right, we observe that the angle of 75 degrees is equivalent for me, the distance that an object will travel, the total range, is the same as if I was projecting it at an angle of 15 degrees. So this is interesting because this means that if you take 15 degrees and add it to 75 degrees, you get 90, right? So, and all of these add up to 90 degrees. Both of the complements of the angles. So 75 plus 15 is 90. 60 plus 30 is 90, right? 60 or 30 gives us to the same place, right? 45 and 45 is 90, right? And you can see that the other ones are the same. So here's a couple of things. One, we notice that the farthest an object will go, and this is in real life as well, is if I angle my angle of attack at 45 degrees. The closer I am to 45 degrees, the farther the object will go. Does it make sense? Yes, because the higher I am, if I kind of go higher up in the sky, if I wanted to go the height, if I want to maximize my height, I'm going to go straight up, right? Straight up. I'm not going to have any energy across the x-axis. If I want to maximize my distance, though, I can't go straight down. It's going to bury itself in the ground, unless I'm on the top of a hill, right? I need to give it a kicking angle. And the kicking angle, the best kicking angle I can give ever is 45 degrees. Why? It's going to be a balance between height and distance. It's at equilibrium, if you will, right? Once we go below 45 degrees, I'm going to get a smaller distance, a smaller range from my origin. If I go higher than 45 degrees or more greater angle, I'm also going to have a shorter range because it's going to go higher up. more energy to the y-axis. I always want you to think about it in terms of energy transfer. Am I transferring energy to the y-axis? Then I'm going to have less energy on the x-axis. If I transfer an equal amount, 45 degrees, an equal amount to the y-axis and the x-axis, I'm going to get the greatest range. Make sense? Okay, let's continue. This is kind of a key learning. If this was going to be on your test, it'd be a question in terms of what's the best angle to fire an object, a projectile at, for projectile motion if you want to get the maximum range. All right, so we know that the maximum range occurs at theta initial at 45 degrees. And then complementary angles will produce the same range. The maximum height will be different for two angles, and the times of the flight will be different for the two angles as well. Right, because the higher the object is, if I put my angle higher, then the flight time, or time in flight, if you will, is going to be greater than if I put my angle lower. If I put my angle lower, time in flight is going to be shorter, right? Because I'm going to be closer to the ground. If that makes sense. I'm just going to mute you, Vincent. Sorry. You're unmuted right now for some reason. Okay. This would not be, this is true. Kira says it wouldn't be true if you're shooting down a hill. Not at all. No, this is only for if you were shooting in a symmetrical motion, if you're standing on a flat plane. This is when it would be true. So again, we want to do the whole conceptualize, categorize, analyze thing, and I highly recommend you break down your assignment into these kind of steps. All right. So when you're given a problem like the Wookiee problem, let's conceptualize what it is. Let's categorize what kind of problem it is, and let's analyze it. By trying to figure out the right variables to use, and then finalize it. So again, it talks about how to do that. Establish the mental representation of the projectile moving along its trajectory, okay, in your mind. So conceptual or mental representation. Confirm air resistance is neglected. And in the terms of your Wookiee question for assignment 1, it's neglected. Select the coordinate system with x in the horizontal and y in the vertical. Of course we're going to do that. And then analyze. If the initial velocity is given, resolve it into x and y components. Break it down half-half. How much is on the x component? How much is on the y component? Right, as an example. Treat the horizontal and the vertical motions independently, and we should, because at the end of the day, when we break this down into a computer program, we want pixels on the x-axis, pixels on the y-axis to get our final vector. Okay. Analyze the horizontal motion with particle under constant velocity model. Analyze the vertical motion with this particle under constant acceleration model, right? Because remember, there's always negative acceleration or acceleration due to gravity for the projectile across all time values. Okay? And remember that both directions share the same time. This is important, right? And once we figure this out, we can share the time frame from one equation to the other. And then we can figure out different things like we did earlier. All right, here's non-symmetrical motion, as an example. Here's what we've been given. We're at the top of a hill. Same guy from last week. Okay, he's just he likes throwing stuff off the top of a building, right? He's at 45 meters at the top of a 45-meter building where he's casting his projectile. His angle of incidence from the horizontal is 30 degrees. The angle from the horizontal, 30 degrees. His velocity initial, right, is 20 meters per second. Okay? How do I figure out his velocity across the x-axis, guys? I want to know his velocity across the x-axis. How do I figure that out? What is the equation that we talked about earlier? How do I find velocity across the x-axis? Well, no one's answering. Hey, Vincent, thank you. So we can say that we know if I was going to break this problem down before we go to the next page, right, or whatever, I want to insert a equation. All right, so here's my equation. Here's my equation. And I want to say that velocity across the x-axis, right, Vx, is equal to velocity, right, whatever my initial velocity is, times cos theta. Cos, I'm sorry, I don't have a theta. I have to go into equations and then go to theta. And somewhere on the top here is my theta. Alpha, beta, there it is. So V cos theta. So we know some of these values, right? We can find out, if I wanted to find velocity on the x-axis only, right, then we can take the initial velocity, which is 20, and we can cos theta, that's cos of 30 degrees. So what's cos of 30 degrees? So I go to 30, and I want to find cos. Okay, now here's something. On your calculators, right, we have scientific. We can also go cos, right? Oh, I said 230. No, 30 cos, right? So 0.866, which makes sense, right? So this is times 0.866, let's say 6, okay? And so therefore my velocity across the x-axis, if I was going to figure this out, if I was going to break it down by components, is not that one, this one, multiplied by 20, which works out to be 17.32. 17.3205. Sure. So why am I saying it this way? Well, take a look. If I have 20 total energy points, I want you to think of this for a second, right? Total energy points, 20. I have 20 energy points. But I can only give a proportion of those 20 energy points to both the x-axis and the y-axis. I'm going to suck up some of the energy because of my angle of attack, right? The same thing goes with my Vyi, right? My Vy initial, right, again, would be V sine theta, right? If I was going to look at this kind of stuff here. So if I go Vy then is V sine theta, right? Sine theta. We have the same angle, but the result is going to be different. So I can sit there and say, okay, well, this is the first thing that I would probably do. Break it down into components, right? So we can say that V is 20, sine, right? And I'm not taking into account acceleration yet, just sine theta, sine of 30 degrees. Let's go back to sine of 30. And you can figure this out. If I go sine 30, it's going to be 0.5, right? So this is 0.5. And we can just simplify really quickly. 0.5 times 20 is 10. So notice that I have less energy on the y-axis than I do on the x-axis. Out of the total 20 possible points of energy, I can only allocate 10 to the y-axis with this angle. I'm splitting my energy allocation down into this part. Most of it is going into the x-axis, actually, and not a lot, or half of it is going into the y-axis based on my angle. Yeah, I would ask you for, again, 4 decimal places. If I don't otherwise say it's 4 decimal places, please. Okay? So that makes sense. And we do that here. We say that, okay, fine, I need this. Once I have V cos theta and V sine theta, then we can start figuring stuff out. I know I can use these equations. Range is V cos theta t, and for on the vertical component, it's 0 times the height, my height, plus V sine theta t plus 1/2 gt. I'm going to leave this for you guys to do. So this is where you fill in the detail here of all the stuff, and you can figure out how long does it take. Well, once I have I've broken down the equation, I can figure out by using the quadratic equation and splitting off my formula that I'm going to have into A's, B's, and C's. If you really want me to do it, we'll do part of it. We already know V cos theta, right? And we can sub in V cos theta, which is 17 point something, right? 17 point, what was it on the other page? 17.3205. Right? T. Okay? And we know that this side, what this side is, it's V sine theta, which is 10. We did that already. We did this part in the previous slide. Right? So this is 10. V sine theta is 10. T. We know the height, right? What's the height? Should I put a negative number in there or a positive number? What did I put on the other slide above? Right? Look what I put here, right? I said in previous slides, way back up here, right? And this is, people get this wrong, right? Way back up here, I said on a single slide, it said, you plug in values of Vx and Vy, make sure the values are positive, right? All right, but what about for the height? Right? The height is a different story, right? So should I put a value that's positive in there or negative in there? It says positive since it's elevated above the ground, but we've seen that if this is where I'm at, this is the x and y coordinates. If this is the origin and it shows me that I'm the origin, then these are values of negative. These are negative 45. So you sub in negative 45 in here. And we sub in a negative value for this, negative 9.8, which is negative 4.9. Negative. The other things, the other values are positive, but these ones are negative. Look, I can't figure out time to sub into the range, because this is what I'm looking for, without solving this equation. The only way that I can solve this equation is to take A, which is this, sub it into there, B, and C, and use the quadratic equation. I'm going to get two different answers, a positive and a negative. When I add or subtract, one of them is going to make sense, one of them won't. Example, I cannot have negative time. I'm not a time traveler. So if I get any negative time value, that is incorrect. Okay? Then I take the value that I get by using this formula, and I sub it into the time value over here because it's the same time. And then I get the total range. That's how I do it. Let's move on. So I want in the essence of time, I've got to move on. If you have time, I'll come back. So questions before we get to uniform circular motion. Does everyone get the idea, the concepts behind what we're doing? Again, you can always hit up our friend Spencer during lab to help you with some of this stuff. He's going to be able to understand and help you out. Okay, I know, as Vincent says, you got to review everything. You absolutely have to review everything. And during your test, I'm going to give you a cheat sheet to look at as well. I'm going to help you by giving you a cheat sheet because you're going to have other stuff to look at. Okay? Uniform circular motion occurs when an object moves in a circular path with a constant speed. The associated analysis model is a particle in uniform circular motion. Again, we're using the particle model. An acceleration exists since the direction of the motion is changing, right? The direction being the vector. If my direction keeps changing, right, then I have acceleration. Okay? So we can say that here we have this uniform circular motion, changing velocity in a uniform circular motion. We can say that V final is equal to V initial plus the change in velocity, right? Change in velocity. So we get this delta V, right? And this delta V usually points towards the center, towards the radius. These are radii, so distance initial, or the initial position and the final position. And this is the delta, the change in angle. Now, once we have this, we have a triangle. If I have a triangle, I can solve the triangle, right, using trigonometry. The other thing that I want to talk about is something called centripetal accelerations. Okay, so centripetal acceleration is acceleration always points towards the center of the circle. So centripetal acceleration is pointing inward, right? There's two types of acceleration at work here, okay? So the magnitude of the centripetal acceleration vector is given by acceleration centripetal is equal to v squared over r. where r is the radius or range away from the center. Okay? The direction of the centripetal acceleration vector is always changing, so stay directed toward the center of the circle. All right? So it's always moving towards the center of the circle, whatever that is. Okay? Again, we're talking about circular motion now. Period. Let's talk about period as well. Period t is the time required for one complete revolution. So I revolve around the circle one complete time. The speed of the particle would be the circumference of the circle of motion divided by the period. Why? Because the circumference is the path around the circle. Therefore, period t is equal to 2 pi r, circumference, over the velocity, over v, the speed. Okay? We have to use speed, not velocity, because in this case we don't care about displacement, because the displacement is going to be the same. If the origin is where it's spinning from, the displacement is not changing. So we don't have velocity, we have speed in this case, which is totally something different. We also have something called tangential acceleration. Say that 10 times fast. Tangential acceleration. Tangential acceleration. In this case, the magnitude of the velocity would also be changing, right? So what happens is the velocity is at a tangent to the circular motion. So here's the path of the particle as an example, and you can see that the tangential acceleration is going to be tangent to the curve, right? Tangent to the curve, pointing towards the center of the circle, but in the direction that it's going. So if I have an acceleration here, and I have an acceleration into the circle, the radius, this is centripetal acceleration, then I have tangential acceleration. Okay. Tangential acceleration causes the change in speed of the particle, and then we have something else called the radial acceleration that comes from a change in the direction of the velocity vector. So there's three types we've just talked about: centripetal acceleration, tangential acceleration, and radial acceleration. Those are the three types, and all related to circular motion. So we can define tangential acceleration as the acceleration t over the absolute value, that's what these lines mean, right? Absolute value of the change in speed over the change in time, okay? And radial acceleration is equal to, so acceleration radial is equal to a negative acceleration centripetal. It's the opposite. So radial acceleration is heading away from the center. We feel radial acceleration when we're going around a curve. So if I'm in a car and I'm on the passenger side of the car, the driver, if I'm turning left, I'm going to feel, my perception is going to feel like, from my frame of reference, that I'm being pushed outside of the car. If my door was open, I would fly outside of the car. The way I would fly outside of the car, or the energy that's being transferred, is because of radial acceleration. Okay, radial acceleration is going to push me out. And the direction is the same as the velocity vector if v is increasing, opposite if v is decreasing. And this is important, if speed is increasing or decreasing. Relative velocity. Whenever I say relative anything, it means when I have two observers, right, moving, relative to each other, right? They don't agree on how we're moving. And so we create something called a frame of reference. Now, this doesn't really make sense from a gaming perspective so much, right? Maybe in terms of, a game object that's the child of another game object. Maybe it makes sense from that perspective. For example, the child of an object may not seem to be moving at all. Its frame of reference, for example, if I have a game object, which is I have a character like Mario, he's the game object, and Mario's carrying something. Let's say Mario's carrying a ball, right? The relative velocity or the acceleration of that ball relative to Mario might be 0. But that ball relative to the game world, that's different, right? So we have this idea called frame of reference, right? And it's when we say that the observer is at rest with respect to the origin, and the origin being Mario. And here we're going to talk about it really briefly because it doesn't really relate to us too much, where I have observer A, here's observer A, measures point P at 5 meters, right? Observer B measures point B at 10 meters, right? So there's two difference. I'm observer sitting in a different spot. I can say that I have a different frame of reference, and because I have a different frame of reference, it'll affect the way that I perceive, the motion. Okay, I just want you to get that. I'm not going to test you on it. It's here for your viewing pleasure. All right, and I'm also not going to talk about relative velocity in a generalized form. Okay, I'm just moving on because this is just something for you. All right, I've put in the back here, this is your homework, and I'm hoping that you're going to do it, right? I would normally do this. If I had you in lab, I would not just do, and this is something where you have to kind of balance your labs. I'm going to talk to Spencer about this. You need to balance your labs between doing a little bit of math, some physics homework, as well as programming. And you have to have both things here, because if you only practice programming, and now especially since I've given you your assignment, and I'm talking to you about a test that's coming up on week 7 that's going to include physics, you need to know some of the programming stuff, or sorry, some of the math that I'm talking about here. So let's try and figure this out. A water balloon is thrown horizontally with a speed of v naught, initial speed, of 8.31 meters per second from the roof of a building of a height of 23 meters. How far does the balloon travel horizontally before striking the ground? Okay, what am I asking for here? Because this is where people get messed up. They're like, wait, I don't understand how to figure out problems. If you give me an equation, I'll just do algebra and I'll solve it. Shubham says range. Yes, that's what I'm asking for. How far does the balloon travel horizontally? I'm asking for what's the range of the balloon, or the distance across the x-axis before it strikes the ground. What do I know? What type of motion is this? If I was going to look at the 3 types of particle motion, what type of motion is this? The first one, right? I'm at the top of a hill and I've got my balloon. I've been given no angles, so there's 0 angle, right? And we need time. It says, okay, so we're given at the top a balloon, and it's going at a certain point. I've been giving you the height. We know that gravity is going to take hold across every point on the y-axis. The acceleration on the y-axis is going to continue for every point y. We know it's negative 9.8 meters per second. We know the height is 23 meters. You can figure these things out by using the equations. Calculate the time with Vy, and then calculate the range with time and Vx. Perfect, Maxim. That's exactly how we do it. And how would I do it? I would break it down into 2 halves. On the x-axis, on the y-axis. The first thing I would do is I would draw the problem. I would try and conceptualize and draw the problem out. Literally draw the water balloon and the roof. I'm at the top of a roof. I've got a water balloon. I got a guy. He's throwing it with no angle, or a girl. How far is it going to go? That's what I would do. Number 2 example. An object is fired from the ground at 100 meters per second at an angle of 30 degrees with the horizontal. What kind of problem is this? Right? What kind of problem? Type 1, type 2, or type 3? Type 2. Very good. Why? I've been given an angle of 30 degrees from the horizontal. That is the angle of incidence, right? I know it's not the maximum angle. My maximum angle is 45. If I have an angle, I'm going to use the equations from type 2 motion. Calculate the horizontal and vertical components. I'm going to break those out. V cos theta, V sine theta. I've been given 100 meters per second. That's pretty fast, right? So V cos theta, V sine theta. We already know what this is, right? I'm going to take 100 times 0.5 for the sine value. So that's 50 meters per second on the y-axis, and 100 times 0.8666 on the x value, which is 86.666 meters per second. That's the x and y values right there. How did I know that? We just did that equation with 30 degrees, right? That's how I know. That's how I remember. Okay, after 2 seconds, we've been given time. How far has the object traveled in the horizontal direction? Now, this is a trick. The question you should ask yourself is, do I strike the ground within 2 seconds? Because if I strike the ground within 2 seconds, I might have already stopped in the horizontal. So figure that part out first. All right? Because if I try and do just vxt or v cos theta t, right, then I would just take 2 seconds multiplied by 86.66, so it'll be approximately 170 meters, right? vxt. However, what if in 2 seconds I fall to the ground? Is that possible? I don't know. Prove it. Do your math. Show it. So that is the next problem. 72. Mary throws a ball to the x direction. These questions are also worded weird on purpose. On the horizontal with an initial velocity of 10 meters per second. Okay. Time elapsed during the motion is 5 seconds. Calculate the height that the object is thrown and the vy component of the velocity after it hits the ground. Wait a minute. But we don't know the angle, right? We don't even know what type of motion this is. We know it's type 2. We know it's type 2 because somehow with 10 meters per second, my friends, we can go 5 seconds. How can I go, if I'm given that the total time, the elapsed time is 5 seconds, guys, there's no way that in 5 seconds I'm going to go straight. If I'm on the ground, I must have some angle. We need to find the angle of incidence, right? So that's important. That's type 2 motion, okay? Next, Adam kicks the ball and the ball does projectile motion. I like this one. With an angle of 60 degrees to the horizontal. That's my kicking angle. Its initial velocity is 10 meters per second. Find the maximum height it can reach. I use the height equation. It's type 2 motion. Next, given an object on a cliff and gets fired given the initial velocity of 10 meters per second, okay? The angle of 30 degrees and the height of the cliff is 10 meters. How far does the object go along the x-axis? What's the range on the delta? What's the delta x? What this type is a type 3 type of motion. It's worded badly on purpose. If you got some weird wording like this, what I want you to do is I want you to break it down, right? I'm on a cliff. Cool. My object, I got some kind of bullet or projectile that's being fired with an initial velocity of 10 meters per second. That's v, not vx, not vy. I got an angle of 30 degrees. Angle of 30 degrees, v cos theta, v sine theta. 10 times 0.5 on the y-axis. That's 5 meters per second on the y-axis. And 0.866 times 10, 8.66 meters on the x-axis. I'm memorizing it because it's the same angle, 30, right? And the height of the cliff is 10 meters, okay? Now I know it's type 3 motion. There's 2 ways to solve this problem. I could use the type 3 equations, or I could break it down into an asymmetrical A to apex and then B to C where it falls down. Type 1 and type 2. Okay, well we know the initial height is 10 meters in this case. Okay, so any questions around this stuff? These are very simple examples. I'd like you to practice them. If you do not practice them, when it comes down to doing your test, it's just going to be difficult. It's not like you can't answer the questions by looking it up online. You'll have full access to do everything online, right? That's the idea. But for you, the most important part is not worrying about finding the answer, but understanding the problem. And if you know that the problem is correct, or how to figure out the problem, then you can apply it in code. If you can't apply a problem in code when you don't know how to break down the problem, all right? Okay, that's it for me for this one. That's 74 slides, and we're just under the 2-hour mark. So any questions around this or assignment number 1 before we go? I'm going to stop recording now, by the way, and then we can ask your questions live.